Using the James Webb Space Telescope, astronomers have spotted a massive and densely packed galaxy cluster. This cluster is so highly evolved it could change the entire history of cosmic evolution, because it exists at a time where such structures were thought to be impossible. According to the standard model of cosmology, the universe built itself slowly. Gravity is a patient engine, taking billions of years to grind raw gas and dust into the massive structures we see today. The biggest of those structures are galaxy clusters, colossal groupings that hold hundreds or even thousands of galaxies together in a shared gravitational well. Building one of these takes eons by any conventional estimate. But the James Webb Space Telescope looked back in time, and it found a fully formed galaxy cluster so large and so concentrated that it resembled clusters we normally find much closer to home in the relatively recent universe. At the American Astronomical Society meeting, astronomers presented the data. It centers on a gargantuan galaxy cluster called XLSSC 122. It sits a staggering 10.4 billion light-years away, which means we are seeing it exactly as it looked just 3.3 billion years after the Big Bang. That period was supposed to be cosmic infancy, a time when clusters were only beginning to piece themselves together out of scattered matter. Instead, XLSSC 122 is already ancient, massive, and strangely mature for its age. It is so dense that its gravity is measurably warping the fabric of space around it. It is now the most distant galaxy cluster we have ever observed bending light on this scale, and by calculating precisely how that light bends, scientists can weigh the cluster's dark matter core directly. Before we go further, it's worth being upfront about the nature of this kind of analysis. Everything in this video is drawn from published, peer-reviewed observations and public conference presentations, and it's offered here for educational context, rather than as a final verdict on how the universe works. That distinction matters because what we're about to walk through are open, active debates within cosmology itself, not settled facts contradicting settled facts. The result, when the math was done, was a genuine problem for standard cosmology. A dark matter core this heavy, this tightly packed, and this well-organized simply should not exist this early in cosmic history. It is too massive, too soon. It leaves researchers with an uncomfortable gap. Our working timeline for how the universe assembled its mass appears to be missing a significant piece. And if a hyper-evolved structure like this is already breaking the rules at what astronomers sometimes call cosmic noon, the natural question becomes, what happens when we look even deeper? What happens when we push the telescope past this cluster, past the era of first starlight, toward the very edge of observable time? That question brings us to something even stranger. You are about to look at the most distant object the human eye, aided by a machine, has ever resolved. Researchers who found it gave it an almost reverent nickname, the Mother of Miracles. So for roughly 13.5 billion years, its light traveled toward us. It crossed the expanding fabric of space, getting stretched, getting redder, getting older with every passing epoch, until those ancient photons finally landed on the mirror of the James Webb Space Telescope. What they revealed is currently testing the limits of our cosmological models. This object is called MOM Z14, and its existence raises real unresolved questions. To understand why this is significant, it helps to slow down and walk through the basic physics. Light travels at about 186,000 miles per second, the fastest speed anything in the universe can move. And yet the universe is so vast that even at that speed, light takes an enormous amount of time to cross it. The universe itself is roughly 13.8 billion years old. For the first few hundred million years, there were no stars and no galaxies at all, just a hot, dense soup of hydrogen and helium spread almost uniformly through space. Cosmologists call this stretch of time the cosmic dark ages. Slowly, gravity did its work. Gas clouds began to collapse under their own weight. The first stars ignited, and their ultraviolet radiation tore through the surrounding fog in a process astronomers call ionization. For the first time, the universe became transparent to light. That transition point, known as cosmic dawn, is exactly what astronomers are trying to observe directly, and it's the reason instruments like Webb were built in the first place. Until recently, the record for the most distant galaxy ever observed belonged to an object called JDES GS ZA50, also discovered by Webb. It has a redshift of 14.8, meaning its light was emitted when the universe was only about 290 million years old. That alone was remarkable. Then a team at MIT's Kavli Institute noticed something unusual buried in existing Webb data, an object that showed up clearly in infrared light but vanished almost entirely at shorter wavelengths, a telltale sign of extreme distance. In April 2025, they pointed Webb directly at it, used its NIR spectrograph to break the light apart into its component wavelengths, and confirmed a redshift of 1444. They named it Maisie's Galaxy. And with that confirmation, it briefly took over the title of most distant galaxy ever observed. We were looking at light that left its source just 280 million years after the Big Bang, at a moment when the universe was roughly 2% of its current age. To put that in perspective, imagine compressing the entire history of the universe into a single calendar year. On that scale, the Big Bang happens on January 1st. This galaxy already existed by January 7th. The dinosaurs don't show up until December 25th. Modern humans appear in the final 10 minutes of December 31st. And somewhere in that final sliver of time, we built an instrument capable of seeing all the way back to January. Moem's F-14 itself is small, only about 240 light years across. For comparison, our own Milky Way spans roughly 100,000 light years, so we're looking at something around 400 times smaller. And yet, it is extraordinarily bright for its size and mass, far more luminous than current models of early galaxy formation predict it should be. The obvious question is how something so young and so compact could shine that intensely. There's a second piece of this puzzle. When researchers analyzed the spectrum of Moem Z14, they found an unusually high ratio of nitrogen relative to carbon. That specific chemical signature is familiar, but not from young galaxies. We normally see it in globular clusters, which are among the oldest known stellar structures in the universe, long assumed to have taken a few billion years to form. If Moem's F-14 already carries that same chemical fingerprint at just 280 million years after the Big Bang, it suggests globular. Cluster formation may have begun almost as soon as the universe became transparent to light, which would meaningfully rewrite the accepted timeline. That leaves an open question that researchers are still working through. What exactly are our models missing about how the early universe assembled itself? What makes this genuinely unsettling for cosmologists, in a productive sense, is that Moem's F-14 is not an isolated case. It's the latest entry in a growing pattern. Since Webb began science operations in 2022, it has repeatedly found early universe galaxies that are too bright, too massive, or too chemically developed for the age at which we're observing them. That doesn't mean the underlying models are broken. Decades of careful observation and simulation stand behind them. It means something in the picture is incomplete. It could be the role dark matter plays in seeding early galaxy formation. It could be a mechanism nobody has proposed yet. That kind of uncertainty isn't a failure of the scientific process. It's the process working as intended. The more Webb observes, the more the universe seems to push back against our existing models, and the record for most distant known galaxy is likely to be broken again. It's less a question of whether that happens, and more a question of when. So how do galaxies like this exist so early in cosmic history? There isn't a single accepted answer yet, but there are serious theories worth walking through carefully. One recent line of research has focused on something unexpected: the rotational direction of large samples of galaxies. By tracing the curve of a galaxy's spiral arms, astronomers can determine which way it's spinning. In a genuinely random universe, you'd expect that direction to split roughly evenly between clockwise and counterclockwise. According to the researchers behind this particular study, that's not quite what they found. And the imbalance, if it holds up under further scrutiny, would sit uneasily alongside standard cosmological assumptions. One of the more provocative interpretations on the table is that our observable universe might itself exist inside a black hole. To evaluate that idea fairly, it helps to understand the basic physics of black holes first. When enough matter collapses under its own gravity, it forms an event horizon, a boundary beyond which nothing, not even light, can escape back outward. Anything that crosses that boundary is permanently lost to any observer on the outside. What happens beyond that boundary, inside the event horizon itself, remains genuinely unknown. This is the starting point for a concept called black hole cosmology, sometimes referred to as Schwarzschild cosmology. It proposes that our entire observable universe could be the interior of a black hole that formed within some larger parent universe. Consider how this connects to the Big Bang. The Standard Model describes the universe beginning from a singularity, a point of essentially infinite density, which is strikingly similar to the theoretical center of a black hole. If our universe really is the interior of a black hole that formed elsewhere, then the Big Bang wouldn't have been an explosion into empty space. It would have been the moment matter collapsed inward and, in doing so, generated a new universe on the inside. That idea carries an interesting extension: every black hole within our own. Universe could, in principle, be a doorway to another universe nested inside it. Some researchers have even suggested this could help explain why the physical constants of our universe appear so finely tuned for the emergence of complex structure and life, on the reasoning that black holes capable of producing stable daughter universes might be more likely to persist and, in a sense, propagate. Proponents of this framework point to a few cosmic puzzles it might help address. Black holes, for instance, are known to carry enormous entropy. which corresponds to an extraordinary density of information and that maps loosely onto the sheer complexity we observe in our own universe. Another factor that shows up in this line of research is torsion, a property described in extended versions of general relativity, such as Einstein-Cartan theory. Torsion accounts for the intrinsic spin of fundamental particles and can, under certain models, influence the curvature of space-time itself. Some theorists argue that this twisting effect could generate a repulsive force at extremely high densities, one strong enough to prevent a true singularity from ever forming. Under that scenario, instead of collapsing into an infinitely small point, a black hole's core could rebound in what's sometimes called a big bounce, expanding outward and potentially giving rise to an entirely new universe on the inside. The rapid recoil following that bounce in this framework is essentially what we've been calling the Big Bang all along. Not an explosion from nothing, but a kind of rebirth emerging from the collapsed core of a black hole in some larger, older universe. It's a framework that would meaningfully change how we think about cosmic origins, suggesting universes might form through an ongoing, self-replicating process rather than a single unique event. There's a related and separate thread worth mentioning here because it comes up often in audience questions, and it's a fair one to ask. If we're seeing galaxies, this evolved this. Early, could our estimate for the age of the universe simply be wrong or incomplete? It's a reasonable instinct. The honest answer from the research community right now is that the evidence doesn't clearly point that direction yet, but it also hasn't been ruled out. What these findings do show clearly is that something in our model of early structure formation needs revision, whether that turns out to be the age estimate, the role of dark matter, the speed at which the first stars formed, or a mechanism nobody has proposed yet. Science tends to work by identifying exactly this kind of gap and then testing every plausible explanation against new data, one at a time, until the picture converges. A second and separate active area of research looks at whether the universe might have a preferred large-scale axis or direction. Studies of how galaxies are distributed and how they move across enormous distances have suggested a subtle alignment that wouldn't be expected in a purely random arrangement. This is sometimes referred to as cosmic anisotropy, and it directly challenges what's known as the cosmological principle, the long-standing assumption that the universe looks roughly the same, statistically speaking, in every direction and from every vantage point. If that assumption turns out to be wrong or only approximately right, it could point toward physics we haven't identified yet, possibly connected to the black hole cosmology idea, or possibly to something else entirely involving how fundamental forces behave at the largest scales we can measure. It's worth being clear-eyed about where this stands. The existence of ancient, massive, chemically mature galaxies this early in cosmic history is a genuinely strong and reproducible observational result. The black hole cosmology framework is a serious, published area of theoretical physics, but it remains one interpretation among several, not a settled conclusion. There's also a more conservative possibility that deserves equal weight. Some of our existing measurements, particularly around the expansion rate of the universe or the rotational behavior of galaxies, like our own Milky Way, could simply need refinement. That wouldn't be as dramatic a headline, but it would be consistent with how cosmology has actually progressed over the past century, through repeated correction rather than singular revelation. Either way, the pattern is now well established. James Webb keeps finding structures that are more massive, more luminous, and more chemically developed than our current models predict for their age, and each new discovery narrows the space of explanations that remain viable. That process, of models getting challenged and refined by better data, is not a crisis for cosmology. It is cosmology functioning exactly as intended. What seems clear is this: the universe is stranger and less fully mapped than most of us assume day to day. These uneven rotation patterns, these impossibly early massive structures, they will likely push astrophysicists to reassess parts of the standard picture in the years ahead. And Webb is very likely to keep handing us the data that forces that reassessment one distant galaxy at a time. There are a couple of other explanations circulating in the research community that are worth walking through with the same level of care, because they come up constantly whenever this data gets discussed, and they deserve a fair hearing rather than a dismissal. One is the idea that time itself may not have flowed at a uniform rate throughout cosmic history. Under general relativity, the rate at which time passes is tied to the density and curvature of the space it's passing through, and the very early universe was vastly denser than anything we can intuit from everyday experience. Some researchers have floated the possibility that processes we now associate with billions of years of slow structure formation could have unfolded on a compressed, effective timescale in that early, ultra-dense environment, which would help explain why galaxies look more mature than their age suggests, without requiring any change to the underlying physics we already understand. This remains speculative and hasn't been demonstrated observationally, but it's a legitimate, testable hypothesis rather than a fringe idea. And it's the kind of thing future Webb observations, combined with independent distance measurements, could eventually confirm or rule out. A related but distinct possibility concerns matter-antimatter asymmetry. One of the enduring open problems in physics is why the universe is made almost entirely of matter. When the Standard Model predicts the Big Bang should have produced matter and antimatter in nearly equal amounts, which would have annihilated each other almost completely. Some researchers studying early galaxy formation have asked whether an uneven distribution of that leftover matter, rather than a perfectly smooth one, could have given some regions of the early universe a head start on collapsing into stars and clusters, allowing pockets of structure to form faster than the smoothed-out average predicted by current models. It's not yet clear whether this connects directly to what Webb is finding in objects like MOAM Z14, but it's an active line of inquiry that touches the same underlying question. Was the raw material of the early universe as uniform as our models generally assume, or did it start out lumpier than we've accounted for? There's also a more fundamental question some cosmologists have raised, and it's less about the physics and more about the framing of the Big Bang itself. The standard picture treats the Big Bang as the origin point of literally everything that exists, all matter, all space, all time, beginning from that single moment. But an alternative framing worth understanding is the possibility that what we call the Big Bang was not the creation of everything from nothing, but rather a localized, extremely energetic event expanding into a pre-existing, far larger space that was already there. Under that framing, our observable universe would just be one expanding region within something much bigger. And the boundary of what we can see would simply reflect how far light has managed to travel since our particular expansion began, not the actual edge of existence. This is difficult to test directly, since by definition we can only observe the region light has had time to reach us from, but it illustrates just how much of what feels like settled cosmology actually rests on an interpretive framework rather than direct observation. None of these ideas cancel each other out, and researchers aren't treating them as competing final answers. They're treated as parallel threads, each one chipping away at a different part of the same underlying mystery. Why does the deep universe keep looking more assembled, more chemically rich, and more structurally organized than a straightforward reading of our models? Says it should be at that point in cosmic history. So the honest, unresolved question this leaves us with is simple to state and hard to answer. Are we looking at gaps in our models of how galaxies form, evidence that time or matter behaved differently in the early universe than we've assumed, evidence that our universe sits inside something far larger than itself, or measurements of our own corner of space that still need correcting? Right now, the data doesn't force a single answer. And that's not a failure of the science. It's exactly the kind of open question this telescope was built to keep asking, and each new observation Webb makes narrows that list a little further, even when it doesn't yet tell us which explanation is correct.